is the author of citation classics in systems, programming languages, and deep learning. He currently runs a learning community for technologists. You can call it think tanks if you're old enough, and very many various names. But it's just for a lot of cool people to come together and think about long-term problems. It's called Pebble Bed. That's the most recent thing Keith and Pam are looking at right now. So Keith, um, over to you. Just very briefly, John, could you raise your hand? Just uh, from point of view of, yep, that's John. And that's our head of software. And Dinesh, who's in the room, he's my co-founder and CTO. Dinesh, you want to just like quickly wave as well?
Okay. Yeah.
Cool. And that's it.
If you're okay, we're going to record this session. If you're okay with that.
Sounds great. Yeah, Google Meet warned me. Thank you so much. So should I go ahead and try to share my screen here?
Yeah, I think it should be open to share.
Wonderful. And does that seem to be coming through okay?
Yeah, and you have in the room people who have, we range from people who are from our manufacturing, running out of our manufacturing lines, designing that, engineering that, as well as hardware R&D engineers, software engineers, and just the whole breadth of people sitting in the room there. So yeah, it should be a great crowd.
Great. So I've given this talk once before, and it was for an undergrad omnibus engineering course at Stanford. So I'm used to giving to mixed audiences of software practitioners and people from other engineering disciplines. And there's kind of a bigram I'm coining here, which is engineering envy, by analogy with physics envy. Just out of curiosity, if I can look at the video for everybody. Have you all heard the term physics envy before? Do you know what I refer to if I say physics envy? And so the in both often social sciences, there's this notion that people wish they were working on physics, right? They wish they had ultra mathematical, ultra theoretical hypotheses and theories that like make these bold predictions that then go out and are you test them and they're true. And if you work in macroeconomics or sociology or even psychology, there's kind of a dearth of those kinds of like mathematicalized things where you like integrate them and the units still work and they make predictions that turn out to be correct and you go out and measure them and stuff. And there's this kind of controversy in software engineering about whether it's really engineering or not. I'm coming down pretty hard for the sake of kind of rhetorical clarity in this talk on the side that it is basically not engineering mostly. That's always been an aspirational tag that very few people have like soberly examined what happens when we make software and said, oh, this is exactly like other kinds of engineering. It's always been something that we wish was true. There are things about software that we've learned over the years that make us more confident in building it. We'll talk about some of those things. But even if you pile all of them on top of each other and you do it all right, it still doesn't really lead to the kinds of results that we expect from other engineering disciplines, in my opinion. I think there are reasons that's true. I don't think it's just because we're all idiots and that we're software cowboys who don't care about doing a good job. I think software people have cared for a long time about doing a good job. But I don't want to give the whole talk away, but that's kind of the gist of where we're coming from here today. In addition to the term engineering envy, there are other like possibly bogus ideas in this talk. I've been doing software for a while, but there's lots of people who think I'm wrong about this. When I talked about this while I was composing the slides, a lot of people brought up a recent a series of blog articles actually by Hillel Wayne, where he sort of comes down very hard on the claim that software really is engineering. His big piece of evidence for this, by the way, is that he went out and talked to people who used to do other kinds of engineering who now do software and asked them, hey, is this engineering? And the ex-chemical engineer who's now pursuing a career in software would come out saying, yeah, it is really engineering. This is like kind of a messy methodology in a bunch of ways, in part because it's people who identify as engineers that now have careers in software. But there's at least one smart, thoughtful person thinks I'm completely wrong. If you care about the ideas here, you should check it out and see which side you come out on. So, spoiling the talk a little bit here, the stuff we do when we make software, for the most part, that isn't what the word engineering refers to. And that's not just because we're all clowns. People, as we'll see, have wanted software to be engineering for 50 years now. So this analogy has been there for more than 2 generations of practitioners trying to make it a real thing. We have ways of making software more useful and more likely to be correct. But even if you do all those practices together, you don't get the kinds of results that you expect to get from civil engineering or from aeronautical engineering or from chemical engineering even. And finally, more importantly, like who cares, right? Like if we're just talking, if engineering is a handy word, why not use it? And that's true as far as it goes. But the fact that we have this as the controlling analogy for how we think about software limits like other fields that might be a little bit more like certain aspects of software. So for instance, there's parts of software that are literally mathematical. Sometimes we can view software as a kind of group creative activity analogous to filmmaking or something. Sometimes software is science-like there can be theories and experiments we can do and things like that. We did a quick intro here. I am one of these computer people broadly. You probably use my code. You definitely use my code. I also come at this like at badly wishing software were engineering in a certain sense, right? Like I am of that generation where, where space was exciting and where big engineering projects were kind of some of the things I imagined myself working on as a professional when I was a little kid. So I would love it to be the case that software engineering turns out to be more than evocative metaphor. I just can't torture myself into believing that to be true. By the way, throughout, like people should feel free to pipe up if there's questions, points you want to debate. I think some of these things are certainly debatable. One of the more tricky questions here that I think I will stick by is that software is in fact among some of the most complex things we make. So for example, I had a bunch of contact with Facebook's front-end application, right? And this is just the server-side part of the big blue website, right? This isn't Instagram, this isn't Meta, this isn't, the Oculus, this isn't everything that's ever been written for at the company called Facebook. This is that website where 40-somethings post photos. That thing's 100 million lines of code. And those are, in some sense, like those 100 million lines of code are all kind of components that interoperate. Microsoft has two code bases that are comparable in size, two separate ones. One is Windows, one is Office. And so, engineering approaches for complex artifacts, we like them. There's all kinds of reasons to desire them. Among them is that software is practical, right? Like we care about it because it has economic value. It lets us do things that we want to do in the world. It's not art for art's sake, right? We don't sort of make software so that other people can weep at its beauty. We make software so that people can accomplish things. And finally, like I do actually sympathize with the perspective that says software just isn't good enough, right? Like it feels like our lived experience is kind of circumscribed by software we depend on that just doesn't work as well as we wish it did. And these bugs are like a big deal. I don't want to kind of laugh them off. They cause real harm. They cost us economic value. They cost people years of their lives in some cases. So the engineering approach, were it available to us, would be very, very desirable.
Yeah.
Cool. So flashback 54 years.
Yeah.
NATO, because basically that previous slide already held 54 years ago. It was already the case that software is some of the hardest stuff people did. It was already the case that it was, this utilitarian, economically important piece of activity. Early computer engineers expected software to be kind of easy, and then were surprised to find that it was kind of hard. And NATO held this conference that they titled the Software Engineering Conference. And this is actually just the intro paragraph from their summary write-up of this thing. It's kind of fun to go back and read this, by the way. I did as a side project for getting these slides together. I actually went back and read it. It's like 5 pages long, because sort of so little has changed in certain ways. But when they founded the term software engineering, they weren't describing a field. They weren't looking at a body of knowledge. They weren't looking at a body of practice. They were trying to come up with something provocative to say. They were trying to say, hey, you goofy cowboy coders who live in your cottage industry of software, you should really adopt engineering practices because, all the reasons we've just been over. So the desire to do this and the observation that it'd be great if it were engineering is at least 2 generations old. Okay, it is not a new thing to kind of chide software people for not being rigorous enough.
Just a quick side question. Even before 68, there was an element of software programming or programming things, right? Like, so for example, some of the pre-Apollo missions that happened, famously, it's been said that they were all supposed to be fully automated, but the cowboys at that point in time said, No, we want to put a person inside that. So what was kind of like, do you know the background of like why this specific term was coined away from like just general programming or computer science as a broad
Yeah,
term?
so people have been programming computers for 20 years at this point,
Yeah,
right? People had general purpose
yeah, exactly.
CPUs since the late 40s. And there'd been this discovery that that software sort of resists uh, correctness, right? There's something about software that sort of tends to be broken. And I think for people who were experiencing this as a very young field at the time, which it was mostly, I mean, there was a lot of kind of craft to the way that software is being put together. And I think the observation that said the same way other kinds of construction, right, evolved from kind of individual craftsmen laboring using a kind of folk wisdom into things that more resemble engineering, that a similar kind of maturation needed to be kicked off with software.
Hmm.
And they were hoping to kick off that kind of maturation. So like perfectly reasonable desire, still a perfectly reasonable desire. It just sort of hasn't worked out that way so far. So we talked about physics envy before a little bit, where if you're in sort of often a social science, but it happens sometimes even in like, it could even happen in biology, for instance, right? Biology doesn't have a set of field laws, for instance, right? There's still elements of biology that are kind of stamp collecting, where it's just a laundry list of like, I don't know, here's all the stuff that can happen, right? But more directly in the social sciences, you wish you had kind of, lists of mathematical facts that describe the domain as well as physics does, right? Where you can differentiate them and integrate them and the units work, and where you can make predictions and go out and make measurements, and the predictions turn out to be right. Where there's such a thing as experimental data that everybody agrees violates the theory, instead of you being able to write a kind of opinion piece about how the theory really predicts it anyway, and things like that. And this kind of physics envy view of things sometimes circumscribes other forms of insight in those fields, right? And so I'm trying to make the claim here that something similar has happened in our software construction world, right? So we would like to be able to predict when a project is going to end, predict how many people it will take, and predict how many lines of code it's going to take, and predict how fast it's going to run. We'd like to be able to model the system under test without having to build all of it, right? In every other engineering domain, you either have literal physical models that you can build, right? You might make a little tiny airfoil and test it in a wind tunnel before you try to make a plane-sized wing. You also can do that mathematically, right? And with computer descriptions a lot of times. We don't even have standardized metrics broadly for software projects. I used lines of code a little bit before, but like that's a pretty messy metric for a bunch of different reasons. When we go out and build buildings, if I want to have a skyscraper built, I can have an architecture firm make a design and then take that design and have engineering firms bid on that architecture. While we have software people that we describe as architects, and I've been one of those people, and other software people that we describe as engineers, and I've also been one of those people, the reality is those aren't actually separate processes. You can't take a software architecture and have engineering firms bid on that, on their implementation of that architecture. We also seem not to know under what conditions a given piece of code is going to work or not work. And of course, like we wish all these things were true, and every other engineering discipline has achieved them. Software doesn't. So why? And this is kind of where I start to get into something that I claim is unusual about the domain, and is the reason that this is actually happening. So be gentle with this part. This is kind of the new idea. Out of curiosity, like how many folks have actually have done a sort of like mathematically oriented computer science course where you like prove that the halting problem is not solvable? Have you ever like, all right, Rohit has, everybody's feeling shy. Okay.
Yeah.
So you can take this like partly on folklore, but the proof's pretty understandable if you're curious about it. Computer programs, you've experienced computer programs hanging, right? Some computer programs fail to terminate, they loop forever somewhere. A hang is always and everywhere a bug, right? No computer program should do that. Amazingly, before there were digital computers, when he was thinking about this with pencil and paper in the 1930s, Alan Turing realized that this kind of hang is the absence of hangs like that would be a criterion for a program being correct. Right? Any program that you can hang is a broken program. And so thinking about a future where computers matter and we're writing lots of computer programs, he was thinking about programs that might automatically check the correctness of other programs. And pretty quickly you hit this result that says it turns out you can't, right? So even in this very narrow sense, you can't prove a program correct. So any broader senses of proving a program correct are extremely hopeless. Pausing. This feels very narrow and theoretical right now, I know. But the spirit of this is your automatic checkers are always provisional unlimited in various ways. What this sort of theoretical fact is trying to teach us about practice is that you don't know if a program's correct without running it. And this is spiritually different than the fields where the engineering approach has been really successful, because it basically preempts modeling. So to be able to tell whether my program's correct or not, I have to build it first. And to be able to tell whether it'll work with my user's data or not, I have to use it with my user's data, because most bugs are data dependent. So in practice, there's this term of abuse about sort of supposedly slipshod cowboy software engineering of testing in prod. But the reality is that all software artifacts are finally tested in prod. You can do a lot of things to increase your confidence before then. You should do them. They're cost effective. But we end up finding out software works by putting it into production ultimately. So anybody, I'm going to pause there. This is a weird claim. This is sort of the core of like why I'm pessimistic about software construction having the tight bounds and estimates and shared units and things that we have in other engineering fields, at least pervasively.
So I think they have similar issues in other engineering disciplines. So I'm from Sydney, and the Sydney Opera House is a famous building, and it was an architect guy named Utzon who designed it and won the competition for the building, and he ended up leaving the project halfway through out of complete frustration, because while he had the concept of the building and the idea of the design, to actually engineer it was incredibly difficult, and at some stages was thought impossible. And in the end, the way he had designed it, and part of the reason we were leaving, is that the building wouldn't function for what its intended purpose was. So it wouldn't function because the number of seats weren't sufficient to make it economic or viable, or the sizes of the stages, etc., were not sufficient. And so there was a huge amount of argument, frustration between architects, designers, engineers, and ultimately the group that was paying for it, that was going to have this building at the end. And so in the end, Utzon walked off the job and just said, I'm not going to complete it. And he never came back to actually see the building completed at all. And it's very similar to some software projects where, you know, someone comes in and it doesn't really meet the requirements of what the intended stakeholders were. What we're trying to create, you know, hasn't really been necessarily prepared in that way before, and you end up with the wrong project. And the project itself was supposed to complete in something like 3 years. It took about 13 years to complete. So as much as there are software projects, and we talk about software engineering, as a discipline, we shouldn't necessarily start from a premise that the other engineering disciplines have got things 100% right necessarily either.
Yeah, I mean, here in San Francisco right now, we've actually had a couple of very prominent kind of large-scale construction in 3D projects go rather badly. There's a skyscraper that went up 10 years ago that's leaning more and more. There was a Salesforce park downtown that had a bunch of sort of engineering issues with it as they actually tried to open it to the public. So it is certainly true that there are like examples of engineering projects gone horribly awry in other disciplines. I think if you applied those project standards to almost the median software project, though, it would be considered a disaster. Like the median software project kind of, overruns most estimates by greater than 2x. And taking that into account doesn't seem to be sufficient to get better estimates, oddly.
I think there are more stories and stories like that in software apps and around other disciplines.
Yeah. So I wanted to talk some too about ideas that seem super promising that I claim have had limited utility in the software domain. So I'm gonna start using the term real engineering without sort of scare quotes anymore here. So bear with me. So in real engineering, there's a notion of specification that seems to really accomplish something, right? So there are things like technical drawings, manuals, blueprints, formulas that completely specify enough that you can go out and execute to the specification. And when we've tried to do the same thing with software, people occasionally come up with formal systems for coming up with specifications, but those formal systems end up, if they're good enough to actually specify the behavior of the software minutely, they end up being another gosh darned programming language and falling into the tar pit of sort of Turing completeness that we just described. Right, so you end up building it. Now you're building it in this new modeling language, but it seems to have the same problems that all other software projects actually have. And this is like a funny thing this is one of those things that actually has a cycle to it, by the way. Like every generation rediscovers this, like every generation comes up with its own formal modeling thing, and then sticks with it for a while before they realize they're programming the whole system in this new language and it still has the same problems that software has. An interesting and really intriguing part of software that's a little different from a lot of quote unquote real engineering is that these are mathematical objects, right? A computer program is actually a digital thing. And it's a kind of mathematical object that, at least in principle, you can prove theorems about. If you kind of imagine a small enough program, it is possible to manually construct theorems that say it's correct, at least with respect to some model of correctness, right? And for a while, and this is still an active area of research, by the way, there is a strain of people excited about software correctness who think this is the way forward, right? That if we're able to prove small programs correct, maybe we can automate that, maybe we can scale that automation such that we can actually prove really big software programs correct. So this is still an active area, but the two challenges here that have proven really, really difficult as things go on is, first of all, there's a combinatorial explosion of proof complexity here as you add complexity to the program, because fundamentally, while you make efforts at compartmentalization, if you want to prove that this part doesn't interact with that part, no matter how far apart they are, there's no inverse square law that helps you out here, right? You really have to have as part of the proof that they don't interact in some way. And the other part here that has been even more difficult is, as we'll see, like a lot of the energy that goes into software is actually changing software. This is sort of different than building a skyscraper. Once you kind of have built a skyscraper, you go into maintenance mode, and maintenance has a different kind of cost structure and different set of recurring challenges. Whereas almost all of the cost of a program is like after its initial construction. And this could be, this seems to be part of the structure of the universe. It's probably beyond the scope of this talk to say why that's the case. But I think it's intertwined with everything else we're talking about here. It's not just bug fixing, though. It's also adding features and things. And at least in principle, as soon as you change this mathematical object that you've got this nice big correctness proof about, that proof is garbage and you need a new one. So if we ever want to have correctness proofs be part of the story for how we have lots of confidence in most of the software we write, we're going to need to have proof maintenance the same way we have program maintenance. And this is still kind of blue sky research right now. I should say here that one of the things that's changed during my lifetime as a software practitioner is that there are kind of real systems with this kind of proof now. One of them that I'm aware of is the L4 microkernel. There's a version of the L4 microkernel, which is like a tiny operating system, basically. There's a version of that tiny operating system that actually is proven correct for some uses. a good first order of magnitude guess is like that it'll cost about 100 times more to construct software that way. Right? So like given your million line program, it would cost you what it would cost to develop a 100 million line program or something like that. That's a, has problems. There's no standard units again. But that seems to be about the right explosion in cost. So this is not currently seen as a kind of scalable solution to all of software.
Quick side questions. Isn't this a solved problem in physics where we've known quantum mechanics and general relativity, but because as you go to higher order and you have emergence, small order scale laws don't scale up that well. And I think this is also kind of proven in the Conway's game of life, right? Where you start from a very one of basic principles, but as you scale that up, it just becomes impossible to follow the same kind of rules and principles. Wouldn't that also be true here, where even if you could prove mathematically small programs at higher order or bigger lines of code, emergence would appear?
Interesting. I haven't thought about the emergence angle here. There might be something to that. My initial, but I'm like not inclined to speculate initially.
Right.
There's a much like simpler, less kind of less conceptually rich sense in which it falls apart, which is just like it has too many moving parts, and you need to separate all those moving parts, even at the lowest level of abstraction. Even though, yeah, you're right that emergence might be the next challenge if we conquered that one. There's a perspective on software that's very old that says this is sort of related to the specification perspective too, that the problem is that we didn't know what we were building in the first place. The problem is that we just didn't sort of think clearly enough about what we really needed to make. And if we had a really big upfront process for figuring out what we should be making, then we'd write the right thing the first time and we wouldn't spend all this money changing it. And we could afford to build up a proof as we went and so on. So this has led to a model that almost nobody uses the term waterfall because it's become a term of abuse in software. But waterfall does describe a particular method that organically occurs when you find yourself nervous about a new system and kind of procrastinating about beginning to implement it in a way. It starts with sort of going out and talking to users about what they need, and then building some large-scale design, and then taking that large-scale design and handing it off to implementers. That part doesn't work, by the way. You end up having to iterate on the design at that point. And then taking the implementation and handing it off to testers. That part doesn't work because you end up having to change the implementation and the design because of the testing. Taking the tested artifact and deploying it, that part doesn't work because you end up testing in prod, and so what you deployed changes what you have, changes your notion of the requirements, the design, the implementation, the testing, and then you go on to maintain it, which of course also takes you back to step one over and over again. And basically, the short version of this is that you figure out all the real problems in the last couple steps of it, and they can send you arbitrarily far back into the beginning of it. So rather than trying to do all, this whole gigantic system at once, work it through this nice long pipeline and never backtrack, we need some kind of different approach. A lot of people think that testing is the problem here, right? At some level, why are we worried about proofs when you can write a list of how the program's supposed to behave and just go out and check that the program actually does that? And the problem here just ends up being another combinatorial explosion, and this time it's usually an explosion of program state. If you imagine kind of a simple, something like a PDF editor, and it has a little dialog box when you go and save the PDF that says, hey, should this be portrait or landscape? Should this be black and white or grayscale or color? And should it be a couple of other things? That already has, hundreds of states in it. All of which need to be tested separately. So if you want to sort of, usually exhaustive testing is not a workable strategy. If you want to do something like this, perhaps you can enumerate all the behaviors and then sample the states and try and convince yourself that the sampling, is trending towards, will eventually catch most of the bad cases. But it is always possible that there is a 1 in 4 billion in the 2 to the 32, possible states for some of the 32 binary features. I'm going to pause here. These are all techniques that have advocates still. They're probably techniques that in particular enough circumstances merit thinking about, but they have been proposed as kind of general cures for the problem that software doesn't work very well and that we can't estimate it. The next section is a set of techniques that I think do work, with the caveat that even taken all together, it doesn't get us a field theory of software, right? It doesn't get us a set of equations. It doesn't get us unified measurements. It doesn't get us everything we wish we had from a mature engineering discipline, let alone estimates, right? And by the way, I'm kind of grounding these in empirical experience, both my own and kind of oral experience from other experienced software practitioners. A learned experience here is that constructing software isn't that hard. It is changing software where all of the energy goes into. And most of the change that a software project undergoes during its life cycle, we didn't know about when we designed it initially. And there's not really a foreseeable path whereby we would have known about it before we had to introduce it. So for example, if you are writing a user application and that application has a 5-year long lifespan, at least in the technology industry as it exists today, there are going to be things like iPhones that are invented somewhere in those 5 years. And you are going to have to accommodate that kind of, extrinsic change in the ecosystem. Yeah. And there is no way that you could have done so, while requirements gathering 5 years ago. Everybody cool with this view of things? There's a pattern that kind of emerges from that world, where we strive to always basically have a working system. And that could be literally 1,000 lines of code that a founding engineer puts down under a very tight time constraint early on. And then, since that system's going to have to undergo a lot of change, it's not very complete because the world's going to change around it. You build layers of defense around the functionality that it currently has. Right? You automate that defense as much as possible, but there might be some manual steps in the way there. And so the idea there is that we're going to, take on these costs and risks of changing it, but we're going to be constantly growing and expanding that defense as the surface area of the program grows, to try and, first of all, keep it working as well as it did before, and secondly, keep it as safe to change as it currently is, and hopefully make it even safer to change than it is. And then finally, a chunk of this, since ultimately all change is tested in prod, it means that we have to deliver the change in small increments. Right? It means that we have to deliver a little bit of new stuff to users at a time, instead of delivering in big bang, here's the new universe, here we were on 2.0, here's 3.0. Those kinds of changes are associated with a ton of chaos and a ton of user pain. So this approach has a couple names, by the way, like you'll hear this referred to as agile and stuff like this, but like you'd have invented it yourself if you spent enough time in software over the last couple decades, trust me. You might have given it a different name, but this isn't just some crazy thing people dreamed up. It's like it's a consequence of the forces that are brought to bear on normal software projects. So this leads to this MVP pattern, right? So step one of making a partial provisional solution lets us have some kind of functionality that we can defend, and then we can get into sort of a monotonous cycle of just improving it, improving the defenses, improving it, improving the defenses, and so on forever. The most important kind of those defenses is automated testing. I'm not particularly opinionated about unit tests versus integration tests versus other kind of tests. I am opinionated about automatic versus manual testing. Do you think you want machines to be doing the work of testing to the degree possible? I care much more that a test increases my confidence as a developer than about any technical property of the test. Right? So one of the ways that the testing efforts fail sometimes is by trying to drive them with metrics like line coverage and stuff like that. Has ever heard of the line coverage metric, by the way? Do you know what this is? Yeah, I basically say like, oh, how many lines of the system under test did I exercise? So if you decide, like as a software leader, I care about testing, so I'm going to make line coverage get to 100%, this quarter. What you're actually doing is freezing the implementation in its current state, because people will write tests that are basically a trace of the way the system happens to work right now, where every F statement gets traced out. And they make it impossible to actually change code meaningfully without breaking all the tests. And so it is much more important that I, as a developer, got more confident from the test than any sort of technically, mechanically checkable property of the test. And by the way, this gets to sort of one of the things from, I'm going to say, real engineering that I think is most valuable for software people to take away, which is not a technique, not a mathematical thing, not a professional standard per se, other than an ethos, right? And that ethos is like, you have to care about what you're delivering, right? You have to care that it does what it's supposed to do. You have to be curious about the ways that it might not do what it's designed to do. And you have to be willing to put in a ton of energy and effort to make sure that it does what it's supposed to do. And that is more a professional standard than, you know, a direct idea that you can transplant out of a different engineering discipline. But that, more than anything, I think is the reason things like testing efforts sometimes aren't as effective as they could be. There is no technique or process that the lack of an ethos like I'm describing can't subvert. And finally, this observation that we have to test in prod ultimately is what leads to sort of CI/CD. So there's all these tools. You hear there are conferences about CI/CD. It's a whole space now. It's a space with little subspaces and so on. Tons of startups, tons of products. But the gist of the spirit of this, whatever tool you use, whatever, if you roll your own, if you end up using something that some SaaS company builds, but the spirit of this is that you rely on your automation and your testing to let you deliver changes in small increments, preferably as close to the time that they're authored as possible. And this feels crazy to people that have, you know, that might be coming from, like, say, an aerospace engineering background, right, where the process of delivering change is very deliberate and very careful, and the pipeline between coming up with a new idea and it being in customer hands is very long. But I want to offer a kind of manufacturing perspective on why this might actually be right. And that is that changes that are built and not yet deployed are actually kind of inventory, right? They're kind of cost. They're a debt that you can't see, right? Because someday you're going to have to take these changes that you think work and find out whether they actually work or not by giving them to customers. And as you hesitate and wait, that backlog grows larger and larger, and it's actually a kind of invisible deficit that you build up. So CI/CD can also be thought of as a kind of debt management strategy that says, no, we want to keep that debt as small as possible, for all the same reasons that, you know, in queuing theory, you want to keep queues short. We want to keep the stuff that's in that backlog of undelivered change really, really small. And finally, this isn't sort of, this is more of a nouveau thing. This isn't part of classical Agile. Monitoring and observability are, you know, are one of the practices that you can adopt and set of tools you can adopt that will make you safer. These don't directly, this is more about our ability to act after the fact when we've delivered flawed systems than about our ability to prevent delivering a flaw. But the reality is we are going to test in prod and we are going to discover problems in prod. So we'd like to instrument our system in such a way that we can understand what's going on. And again, this is a whole space with whole products and whole startups associated with it. I'm actually a big fan of Honeycomb. It's a free plug for them. I don't have any skin in the game. I just think they did a good job using some of the ideas here. But even if you roll your own, the important part here is instrumenting and monitoring code is part of the process of engineering it for production and making it in a way that's going to be serviceable. So just reiterating here, MVP, defending current level functionality, improving it, and then iterating 2 and 3 forever. So I'll pause here. I think this is literally a repeat of the TLDR. I'll thank you all for your time here. It looks like we still have something like 6 minutes, assuming we had an hour to talk some more, and I appreciate your patience.
Thank you, Pat.
Guys, we can't hear any claps, but it's all right. We got the spirit.
I saw the claps at least.
Saw the claps. Awesome. I think what we are going to do is hand it over to the room. I'm sure There's tons of folks there who have maybe some questions. So John, do you want to just take that?
Yeah, I think on our side, you've got a lot of experience with Slack and with Facebook in terms of, I think, taking stuff that was probably small to start with and then expanding out and growing massively. And for us, we've got software and platform work that we're doing at Pebblebed, which is smaller scale. We've got a plan for what happens to be larger scale.
John, John, you're a bit far from the microphone.
Okay.
You want to just like move a bit? Yeah.
I'm over this way.
Oh, excellent.
I was just saying that for us, we've got a small software engineering team, but we have to plan for growth ultimately as well and how we're going to scale. And so I'm interested in any thoughts, experiences that you've had through Slack and through Facebook around that balance between doing what you need to do now from a feature function point of view, but investing, architecture-wise in the future, and how you make a balance between we can't do 100% features and no architecture, but we can't do 100% architecture and no features at the end of the day. So
Right.
It's difficult to get that balance right a lot of the time, or to create technical debt, while you're doing that. So any maybe thoughts, ideas, or background that you've had in your experience balancing those things out?
I think that balance is almost the entire art of professional software engineering, as we currently deem it. So I think that's a really key question. A good friend of mine named Kent Beck is a fellow guy at Pebblebed, by the way, is busy writing a book right now called Tidy First ? And it is about what he claims is the question software engineers ask themselves 20 times a day, which is, I have to make this change. Should I clean up first or not? Like, should I do it directly in the messy code base as it is, or should I make a different change that that makes the change I'm going to make easier? So first observation, there's two kinds of change that you make. One kind of change improves functionality in some way, and another kind of change doesn't, right, is a structural change. I'm going to say that the second kind of change, unless we're artists for art's sake, right, unless we're aesthetic software builders, we always make that second kind of change in the hope of making that first kind of change cheaper, safer, easier in some way. So that means that good design is always relative to some trajectory through the future. It's a good design is always a good design is one that it facilitates the changes you actually end up making. That means it makes some other path of changes harder, right? There's kind of a counting theorem here that you can't just have an objectively good design. So you always have some opinion about what the future is there. And that trajectory will always turn out to be wrong sometimes. So those are a couple of kind of mealy-mouthed generalities, but like that gives us a coordinate space to work in, right? I'm adding functionality, I'm making adding functionality easier, and those are the only two kinds of changes we want to make. By the way, I'm an advocate for like having those be separated and having those be perfectly clear about which one you're doing when. Even if you decide to tidy first, those are two different changes. Right? There's the one that doesn't change the system and that just makes it easier, than the one that makes the change. So signs that you are, the signs that an investment in architecture or design or large scale design are needed are actually evident in programmer behavior. So there's a really good book called Software Design X-Rays, which is an incredibly terrible name for a book. It's by a guy named Adam Thornhill, and it sounds like it's going to be one of these like patterns books or something, like a list of like things that are good or bad or something like that. It's actually way more interesting than that. It's kind of a collection of behavioral metrics, which are ways to tell how your team is interacting with this code base. So first observation here is that you've hopefully adopted source control, right? Actually, that is so widely adopted, I don't even think of it as one of those things that we know helps now. But if you're not using source control, use source control. Now that you're using source control, you have this database that actually joins human behavior with the technical artifact you have. And so some of these things that people talk about in design books, like coupling and cohesion, which sound very abstract, you can actually look at what people changing your code base end up doing and measure these things. So coupling, which means like that when this thing changes, this other thing over here has to change, or maybe these 10 other things over there have to change. Generally considered a bad thing. Coupling shows up as changes in the code base that are spatially correlated, right? Every time somebody touches this thing, they also touch these 3 other things. And that kind of jumps out at you once you start running his little shell one-liners on your Git repository. Cohesion, on the other hand, which is like the conceptual unity of a file, that often shows up in a strength of association between team members and chunks of the code. Or if something is coherent, then there probably are experts on it, and there probably are people. Whereas something that gets touched by everybody is probably incoherent. If you graph the functions in your code, or the files in your code, or the directories in your code, or any unit of aggregation, and say how many people changed it last month. This is true in literally every real code base I've looked at. This is true of the Linux kernel. This is true of Slack's code base at the time. True of Facebook's code base when I had the ability to look at it. True of every open source project I've bothered with. There is always literally a very clean power law distribution, right? Where there is one function, one file, one directory that gets changed, big integer X more than the next one down, the next one down, and then the long tail of average ones. That is often a place to sort of, whatever physical part of your code base that is, that's often kind of a place where some framework might be in order. In the Facebook code base, there was a function named something like photos upload, open parens, 26 parameters, close parens, and then like thousands of lines of stuff between curly braces. And nobody knew what this thing did. Like everybody who had to change its behavior in some way just kind of like held the laptop at arm's length and tried to find the general part of it that seemed to be related to what they were doing, and added a 27th parameter, and then changed all 9,000 colors of it or whatever, and then got on with their lives because they didn't care about this thing. So finding things like that are becoming these kind of centers of possibly cancerous growth. This is actually measurable and possible and stuff you can put in spreadsheets. It just isn't sort of very widely adopted as such. So, and by the way, like I think if there ever is sort of a science of programming that lives up to the name, it's going to end up being a social science, at least for the foreseeable, because a lot of it is about applied psychology and is about how humans behave in groups. Because humans are the only way we know how to make software right now, and non-trivial things require groups. So this kind of stuff, if it sounds like I'm kind of discrediting the earlier parts of this presentation, great. I mean, maybe I am. Maybe there is an engineering approach waiting out there. But even if this kind of thing worked completely, there'd still be like units that involve things like people and other things that are not very engineering-y.
Other question?
Sorry for the rambling answer.
It's good.
Yeah.
By the way, Keith, I know it's super late for you. Just anytime you want to go off, just say.
Oh, I don't know how constrained we are on time on your guys' side. I think we're like 3 minutes over your slot or whatever. I'm going to be up for a while just because long story.
Okay.
But,
Yeah, I think like guys probably want to like have some questions. So, John, or what do you mind?
Yeah, hi, Keith. Just wondering, when you're talking about coupling, are you sort of advocating mono repos to sort of achieve something like that?
So coupling can occur in different source code organizational styles, right? So coupling can occur across repositories, for instance. It doesn't have to be in a single repository. I happen to have had pretty good experiences with mono repos, or like at least macro repos, let's say. The 2 software shops I've had the most influence on were both sort of duo repos on their backend, right? So both Slack and Facebook kind of had backend repos that were written in a native-ish language, written in Go or C++ or what have you, and then kind of one big application that really was kind of a macro repo. And in some ways, like both of these places were kind of microservice shops in hindsight, although in Facebook's case, it was before the term microservices was in vogue. So that happens across code bases, that happens across languages even, right? Like if you have, if you change an API, right? Or if you change the performance requirements of something, that can be a form of coupling too. So it's pretty abstract. It's pretty decoupled from physical representations or source code representations. It's anytime a change over here logically necessitates a change over there. Crazy example of a super typical example of coupling that crosses kind of code base boundaries is when people want to do database migrations, right? If you want to change the schema for a database, want to add a column, change the semantics of a column, change age to be age underscore deprecated underscore do not use me or you'll be fired underscore, etc. Those migrations kind of inherently involve a little bit of coupling between at least the database schema and how the source code uses the data in the database. Binary representations of stuff, right? Like if you're compressing things in memcache and before you stored them, uncompressed, that can be a form of coupling.
Yeah, I guess I was sort of thinking more along the lines of a commit when you were sort of saying that things are changing in multiple places, but it must be much harder to figure out if you've got commits in different places, for example.
Yeah, I mean, if the question is like, do I like monorepos? The answer to that is yes. Like, but that's a more controversial and different discussion. And I'm, happy to go down that rabbit hole if that's where we're going. But I know I'm in minority about this these days. So.
Yeah, no, it's fine. I don't like it, but
yeah.
I'll let someone else.
I think a lot of fans of monorepos here.
Oh, great. Yeah, like one of the things I really liked about the monorepo experience was like that I could have all of the tests that I break when I change a library component in one place.
Yeah.
So
not only monorepos, but also monolithic applications here, because a lot of the times we run bare metal high performance stuff on the device itself, which has to be power efficient, compute efficient, all of that stuff. Yeah, so it's a lot of the times like a monolithic repo with monolithic kind of runtime is probably the most ideal as well.
This is, I think they've given talks about this. So this isn't, dirty laundry, but Facebook's microservice collection is a monorepo, even though they are separate services and sometimes in separate languages. It's in one big repo called FB code.
Very cool. Any other questions from the room, guys?
Yeah, there's one question from one of the hardware team members. So saying if software engineers are not really software engineers, what should we call them?
I think what was good enough for Knuth was computer programmer. And I think like when I have the chance to choose my own title for what it is we're doing, computer programming is probably what I'd choose.
But they may have some more creative suggestions, but
yeah,
we'll talk about that another time.
That's right. I mean, so in terms of metaphors that I actually think are possibly fruitful that this blinds us to, and this is like not kidding at all, but landscaping, right? Scientific forestry. I think like some of what you're doing with computing is actually dictated by the environment, quite literally, which we don't have control over and which changes violently. I think medicine is a good example of a field that is practical, right? We rely on a doctor to actually make us feel better today, whenever we show up, whatever the state of scientific knowledge is that day, whatever drugs they have on hand, and so on. But is still scientifically informed, and I think a lot of times, especially people acting in operational roles or in SRE roles, are in a kind of medical-like capacity where they have an actual fire they're fighting and only have certain tools to work with and certain knowledge to work with.
We could be software surgeons.
Sorry?
We could be software surgeons. That sound has a ring to it.
and actually, in the Mythical Man Month, Fred Brooks did propose the metaphor of a surgical team and proposed like an organization of software teams that was modeled after the way that surgical teams are operated, where there would be, a head surgeon and a person that takes care of the tools, and a person who's there to do suction, and a person who's going to sew up afterwards, and so on. And it's we've had a lot of time to figure out whether that works very well. If it worked so amazingly, people would be doing it, I guess. But I do think there's other disciplines to learn from and take inspiration from.
Okay, very good. Any last questions? I think we're just about out of time.
I'll throw one last one to Keith. Since the beginning of Trunk Semester, we have spent a lot of time thinking about, because it's a mix of hardware and software people, and there's lots of we've done a lot to kind of bring some of the MVP best practices in the software industry back into hardware iteration and hardware MVPing, right? You'll be surprised, there is a shockingly minimal amount of literature out there on rapidly building hardware prototypes and getting it out there, and the framework around that. Amongst all the kind of like both in software engineering as a, or just generally architecture ideas that you have seen, any top idea that you think could translate over that barrier quite well? Like, of course, the generic ones are agile and all of that stuff, right? Like, and then that's okay.
Yeah. I mean, there's that whole paradigm, I guess, right? But
Testing in smaller modules, we do that on our manufacturing line, and then we
yeah,
do
modularity is not invented with software, right? Like modularity is one of the ways that we make all kinds of complicated systems work. That's a great question. I think that I mean, the more software-like things are, the more directly applicable it is, right? So if it's an FPGA that's the physical substrate for this thing, then you're really sort of are doing software in a pretty deep way. Let's see. That's a great question. So, I mean, by the way, like, I know this talk is like full of these kinds of like old man abstraction nonsense or whatever. Like, there was a time in my life where I was like pretty near the hardware software interface almost all the time. The beginning of my career was mostly doing hardware bring up. I ported Linux to the i960 for the first time. I did IRIX bring up when I was at SGI and a bunch of new hardware. When I was at VMware, we were kind of emulating x86 at the lowest level. So I am exposed to at least the software interface that hardware presents a lot. And I think that part of things is, let's see. An instruction set architecture is in some ways like one of the best examples of like an architecture implementation distinction we've really made as like a field of computing. I think there's a really clear, lots of examples of people building radically different implementations of a CPU architecture and actually being able to get very deep software compatibility with things as long as they adhere to the right instruction set architecture. It's a kind of a triumph, right? It's one of these interface implementation distinctions that's been really, really successful. And I would be curious whether there's some ways that you can preserve that and allow a lot more flexibility in how you do expose the hardware functionality. So basically, if you would carve out sort of some of the instruction set as being much more deeply optional and have some integration with the software stack that kind of understands that. This exists right now in the forms of like accelerators and stuff like that, right? Like in the olden days, you could write code that would like check if you had an FPU or whatever, and it would run different code if you had an FPU. The moral equivalent of that and that kind of hardware, that kind of acceleration style of things, I think is very, very underexplored, in part because the software is such a headache right now. But kind of the end of Dennard scaling, right? The end of clocks just getting faster every year means that we're going to have to do more and more of that to actually keep delivering more performance, I believe. And we're going to have to do more and more kind of hardware, software co-design and application-aware hardware design. So some long way of saying my best guess is like making it much more safe and cheap to play around with acceleration APIs and play around with instructions, parts of the instruction set that are a playground where you can mess around.
Yeah, because I mean, like nowadays, everything is like kind of abstracted to higher level APIs, right? So you don't really get access to lower level instruction sets. And even if you do get access to that, it's super esoteric most of the time.
Yeah, I mean, even NVIDIA's CUDA, right, delivers it through a VM, right? The CUDA bytecodes that you get compiled into your binary to run your GPU. That's not for the GPU you actually have. That's for some virtual machine your GPU implements that like has some impedance loss between the actual hardware there and the virtual machine that they target. So,
interesting. Awesome. That was a great answer. Thanks, Keith. Thanks for your time. I know it's super late there. Thank you for taking time out.
Yeah, thank you guys too.
Let's give Keith a
round. That as well.
It must look really terrible if you guys keep going on about how late it is here. Like, is that? Am I looking that haggard here?
No.
Okay.
We don't function as well in the middle of the night as you do. That's all.
All right. Thank you for for your patience, everyone, and hope this is worth your time.
Thank you.
It was great. Thanks, Keith.
Bye-bye.
All right. Take care. Bye.
Thanks,
Hey.
Ravi.
Yeah. I'll get Keith to share his slides.
Okay.
Yeah.
Cool. Yeah. To get back on track.